All of you, welcome back to Organic Chemistry 2341. Right here after our recent events, I want to make sure that you reach out and talk to your friends and seek counseling if you need it, or just call somebody you haven't talked to in a while and just vent with them. And so we've all been through a lot lately, and what I would hope to do is that if you need something, go ahead and seek something. Those of you who are doing, well, it's still talk to somebody anyway, because it's something we as humans all need to do. Okay, so welcome back. I'm going to go ahead and start with our organic chemistry. We're going to finish up module 4 today in preparation for our exam on Monday. You will receive an email Monday morning about the best way to take the exam. The exam is on Top Hat. Top Hat suggests you close everything, reboot your computer, and have only Top Hat or your Google Chrome and Top Hat open at the same at that time. And it tends to take any issues that happen, like switching Wi-Fi's and stuff like that, which kicks you out sometimes. It solves that a lot of the time. I will be live monitoring from 12:30 all the way through the end of the exam. So if you are having issues, email me. I will be here and I will monitor that and try to fix any issues you might have with your exam, okay? So, but again, the format is multiple choice. It's going to be, I believe, 30 questions over the first 4 chapters. The total possible points available is 130. So don't look at whatever number you get and say, oh my gosh, I got a 72. It's like, no, that's a raw number, and I will do that to you, and you. That's just the raw number. I actually do a statistics average on there. You should not be making 100 on this exam. So if you are, I know you're cheating. So, but do your best, and we will scale it to see how the class does. Okay. Now, you do not come to the Zoom class. You go directly to Top Hat. You go to the exam. When you open it up, you should be assigned one exam. It's either going to be A, B, C, or D, depending on whether you have ODS accommodations or the luck of the draw of which exam you got. So you'll go ahead and you should only see one. They should be assigned to you individually so that you don't have to worry about that. And you'll be able to log in with Proctorio. It's going to have you pick up your computer and scan the room, show that you're there by yourself and you don't have anybody helping you. And then you'll scan your ID, and then they'll let you start the exam. If something happens, like there is a dog runs through the background, that's okay, because what it'll do is it'll flag the AI and tell me to review the video. And if you're doing something suspicious, we'll have to have a talk. If you're not doing something suspicious like a dog, well, it shouldn't be a problem. No, in fact, you are allowed to use 2 pieces of scratch paper with your exam. There's a question about using scratch paper. As long as you're staying in the line of the camera where you are, having your scratch paper in front of your computer and answering your questions here, that's what they're looking for. You can have scratch paper, but at the end of the exam, you have to show me both sides of the paper to show me that you're not just copying stuff down for other people. Okay. I don't have a working camera on my laptop. Is that a problem? Email me. I have a workaround for that, but it's not as easy. So it would be better for that. Okay. All right. And we'll get to that. Any questions about the exam so far? Okay. I find it's a lot less stressful than taking it through Examity. I've been told, yes, you need a photo ID for the exam, your student ID, or your driver's license is fine. And again, this is completely AI monitored. There is no live monitoring unless it flags something very suspicious, and I'm the only one who gets to look at it. So don't worry about people yelling at you from across the country or across the world. That's not going to happen on this one, okay? So it's going to be a lot less. Do we have to set up anything up on Proctorio prior to the date? I would just go in and no, if you have Top Hat up and running, you have Proctorio up and running. Oh, no, that's not true. You have to download the plugin. So you want to go to Top Hat and download the plugin and make sure it's up and running, and it'll let you test it. So yes, thank you. I forgot about that. That was so long ago. Okay. Any other questions about the exam?
It'll just be 80 minutes, correct? Just during class time?
It'll be just during class time. So it starts right at 12:30. You'll have 80 minutes unless you have ODS accommodations, and then you can have a longer. Okay. All right, good questions. All right. So what I'm going to do now is I'm going to go ahead and get back into module 4, get us back thinking about chemistry again. And let me share my screen. There it is. All right. All right. Can everybody see the screen? You will get an email on Monday morning at 6:01 a.m. that has all the instructions for that day's exam. Okay. Actually, no, I don't have it recording audio because it records something else that monitors like that. The audio tends to make it buggy, so I just have the video, and it does some other sensing that doesn't have it so buggy. So audio is not required. Okay. All right. I think that answered all the questions. So let's go back and start talking about alkanes again. Remember, when we have alkanes, that sigma bond is freely rotatable unless we have it in a ring. Now, we can use that to our advantage by looking at that thing called that Newman projection, right? The Newman projection is where we have where the front carbon has the pinwheel, the back carbon has the ring, and the things that are attached to the back carbon are sticking off the ring, okay? This Newman projection is very important to understanding that rotation. Now, it's also important to understand why cyclohexane is more stable in the chair configuration, because if we did that, looking down these axes of this cyclohexane, we would see that all of the hydrogens are in their staggered configuration, and the two carbons are in a gauche configuration. That is the lowest energy possible. And that's why there's no angle strain, and that's why there's no ring or torsional angle strain either, or angle strain, because they're all in that most favored position, that staggered or gauche position. Okay. So, and if we did the same thing, if we did that, making the Newman projection on that boat configuration, what we'll see here, and again, we're looking down let me do a wider one, this axis and this axis here. So we're actually looking at it in this direction right here. What we'll see here is that the hydrogens are in their eclipsed positions, and the two methylenes that link them together are also in the eclipsed position. That's why it's so much more energy. It's that eclipsed energy and that fact that we have even these two groups are starting to get very close together. This is why that boat configuration is so much less stable than that other, than the chair configuration, okay? Now there's no angle strain because we still have the 109.5 degrees, but those eclipsed parts in that Newman structure tells you it takes more energy to have that configuration, okay? The exam will be over chapters 1 through 4. All right. All right. So how do you draw this silly little thing? Okay, it's really easy, okay? You have to just think of 3 sets of parallel lines, okay? So when you're drawing this, you want to start with 2 lines that are parallel to each other. And then you want to draw 2 more lines that are parallel to each other. Oops, that's the wrong line. Okay, let me start again. Sorry. It's easy, really, trust me. You start 2 lines that are parallel to each other. Then you draw a parallel line up and a parallel line down, and then a parallel line up and a parallel line down. And that gives you your chair configuration. Now, remember, you have substituents on here. And in the case of hydrogens, what you want to do is you want to draw all your hydrogens in the axial position first. Remember, the axials are going up and down. See how all these hydrogens are parallel to each other? They're all parallel to each other, so they're the axial positions. And then you sprinkle the equatorial hydrogens around the outside, okay? Do not try to get these weird bond angles that look, kind of weird. It will throw you off on the configuration. It's best to do the axials first, like here, and then sprinkle the remaining groups around the outside, okay? When you do this, you'll start to see, okay, that's a pretty interesting configuration. But when I take it and pull one side up and put the other side down, flip it into the other position, you're going to see that all of those equatorial bonds turned into axial bonds, and all the axial bonds turned into equatorial bonds. So let's talk about that a little bit more. Okay, so for this particular experiment, what we're going to do is we're going to colorize all of the axial hydrogens with that blue X right here. So I'm going to do the blue X right here. Notice that all of these have parallel bonds. They're all going up and down. Imagine an axis in the center of your ring here, and that you have an equator going around in that direction there. Okay, so they're all parallel and they're all in that axial position. Now we've sprinkled the Y's all the way around the outside in those equatorial positions. Now, if we were to take this Y and pull it down, and it turns into this Y over here, and take this Y and pull it up, and that'll turn into this one here, what we'll see here is that all of those equatorial Y's become axial Y's, and all those equatorial X's become axial X's. So the cool thing about that is that we can flip them back and forth, and if they're all the same group, we can say whether one conformation will be more stable than the other conformation. Okay, so what do I mean by that? Okay, if we had something other than hydrogen, it's going to take up more room. Okay, so now we will have a competition between which conformation is going to be more stable. Okay, so there's a, if we draw it regularly, it's going to look like this. This is just our standard stick figure showing us where everything is. This little configuration, if you draw it this way just to see where everything is, you will not get where the things are axial or equatorial. We have to switch it to that chair and boat configuration. So the one way to do that is to easily convert from this one to that chair configuration is to draw your chair, do your parallel, 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 parallel. And now notice this methyl group is pointing up. So we're going to put it up to start with. Our CH3 is there. And we can assume that all the other positions are hydrogens. Okay. Now, when we do that, we get this configuration here. Okay. Now, I'm going to tell you that that configuration only exists in liquid methyl cyclohexane 5% of the time. The other 90% of the time, we have taken this axial position and flipped the ring so that it's in the equatorial position. Okay. Why? It's only there 5% of the time if it's on top. It's there 95% of the time if it's on the equatorial position. Well, let's look at how big that methyl group is. When it's drawn like this, it looks about the same size. Okay. Okay. It's more stable, but why is it more stable? Okay. Let's redraw this methyl group to show where its hydrogens are right here. So imagine there's a hydrogen here, and hydrogen here. And these are the two other axial hydrogens that are next to it. Notice how close the interaction is between those hydrogens on the methyl group and those other hydrogens on the cyclohexane. Okay. If we were to switch that methyl group out to the axial position here, come on, go away. We can see that the methyl group hanging out here, I'm going to pull it up over here, is actually is a lot further away from any of the proximal hydrogens next to it. Because that methyl group takes up so much room, it butts up against the hydrogens here and wants to be in the other position. Okay, so it's the other position because the electron-electron repulsion of these hydrogens is closer to these hydrogens in this configuration than in this configuration. That's why it's more stable, that minimizing the electron-electron repulsion. So let's look at that a little more. And let's use that with the Newman projection, okay? So the Newman projection here shows us a little bit more about what is going to be closer and further away than other things are. So if we take our methyl one right here with in our axial position, that first one we drew, and we draw our Newman projection right here, we'll see that we have 1, 2, 3 carbons are all in those gauche positions, right? So we have 3 carbons closest to each other, okay? So, but if we were to redraw that with it in the equatorial positions, let's look at that here, okay? What happens with it is now we have one of the methyl groups is now anti, and only two of them are in the gauche position. Here we have 3 gauche. Here we only have 2 gauche and 1 anti. And what we learned before was that anti is the more stable because they're as far apart as possible. Okay, so do we see how drawing that Newman projection of the cyclohexane gives us an idea of which system is going to be more stable? You're always looking for your large group to be anti to the methyl groups in the ring, if at all possible. Okay. So if we just go from a hydrogen to a methyl group, we see that at 95% of the time, that methyl group is going to be in the equatorial position. Let's look at some other things right here. Chlorine is not quite as big as a methyl group, and that means it only spends 83% of its time in the equatorial position because it's more stable. It spends a good, 17% of its time in that axial position because it's smaller than the methyl group, okay? Because it only has 3 lone pairs coming off, not 3 hydrogens coming off. And if we switch that to so do we want them away from each other? Oh, yes. You want the external, the thing that's outside the ring as far apart from it as possible. If you have a straight chain, you want the 2 substituents in your Newman projection to be anti to each other or opposite each other. The farther away, the better, okay? Now, let's move up from a methyl group to an ethyl group. It really doesn't change all that much because it's the hydrogens on the methyl group here that are starting to take up a little more space with that methyl group next to it. By the time we add another methyl group, it's gotten a little bit harder because now we have 2 methyl groups that are, and 1 hydrogen that can be butting up against the axial hydrogens here. By the time we get to 3 methyl groups on there or a T-butyl group, it spends 99.9% of its time in that equatorial position. Okay. Now, why? Okay, it's all about the size. It is so big at that point, it's going to basically be covering up those axial hydrogens, and therefore it's going to want to be in that more relaxed equatorial position. Okay, so now we see that the cyclohexane by itself can flip back and forth with almost no, just an energy barrier to go back and forth, but they're equally the same. But when we start putting a substituent on there, that changes. Okay, and it has everything to do with the sterics of whatever group you have here coming and hitting these 2 other axial hydrogens. Okay, so what if we had 2 things on the ring? Okay, that's going to be a little troublesome. So let's go through that. So if we looked at this structure right here and we convert it into our chair or boat configuration, what we want to do is we, of course, want to draw our parallel lines. And then let's see, 1 up, 1 down, 1 up, 1 down. And I'm going to draw this as the 1 carbon here. Oh, no, this is the 1 carbon here. And this is the 2 carbon here. Now notice this bromine is a solid wedge, so it's pointing up. So we're going to put this bromine up right here. And that means the hydrogen was below it. And so it's going to be in that equatorial position. Now, in this case, the bromine is down. So I'm going to put that down. And the hydrogen is in that up position, which turns out to be in the equatorial position as well. So this is the conversion from this to this. Okay. See how I use the wedges to tell me where the bromine is going to be on the top of the hydrogen looking this way. The hydrogen is going to be on top of the bromine looking this way. Do you see that conversion? Okay. Because once you get to that conversion, now we have this right here. In that configuration, both of those bromines are in that axial position. Okay, so that's not impossible, but let's flip the ring. What happens when we flip the ring? Well, all the axials become equatorials and all the equatorials become axials. So now we have two bromines in equatorial position. So it's more stable. The two largest groups are in the equatorial position. Okay. Now, what does that look like when we draw our Newman projection? In this case here, our two bromines are anti to each other, but they are gauche to the other attachments. There's 2, 3 gauche interactions here. If we move it to the other side, now the bromines are in their gauche position and the carbons are in that gauche position. We have 2 gauche positions, not 3. Therefore, it is more stable to have those large groups on the equatorial position. Okay. How will you know when you should flip the ring? Well, once you draw the first one, you'll see, is my large group on an axial position? If it is, if I flip it, does some other group become on the axial position? Ideally, if you can get them both in the equatorial position, that will work, okay? But let's do a different isomer and explore that exact question in the chat there. So let's do that other question here. And instead of using that cis, that trans 1,2-dibromocyclohexane, we're going to use the cis where they're both there. So when we draw this, right? So the bromine is going to be on the top, and so the hydrogen is going to be below it. And in the other one, we have the bromine on the top and the hydrogen's below it. Okay, so when we see that, we've been able to translate it into that chair position. And we'll notice that we have one bromine in an equatorial position, one in an axial position. If we flip the rings, our axial position becomes our equatorial, and our equatorial becomes our axial, meaning we still have one equatorial and one axial in both of the configurations, which means they are of equal energy. Okay, so whenever you have one group on there, you always want to have that big group on the equatorial position. When you have two groups on there, you're trying to get as many on the equatorial position as possible. Okay, in this case, it's going to be one or the other. It can't be both equatorial, so they have the same energy. Okay, okay, question on that? I think that answered the questions in the chat. All right, so what if you have 3 groups on the list? Again, with more than one group there, you try to get as many in the equatorial position as possible. Okay, so in this case here, when we draw this, we notice that we start with a wedge. So that one's facing up, a dashed wedge, that one's facing down, this one's facing up. So when we first draw that, we're going to have 2 of those in those axial positions and 1 of those in the equatorial position. Okay, but when we just learned, we want to flip that so that we have 2 in the equatorial position and only 1 in the axial position. Okay, but hold it, they are all in axial positions. That means that that's not going to be the most stable one. It's got to be the other one where we've flipped it such that they're all in the equatorial positions. Okay. But in the case that if you had 1 equatorial and 2 axial, you'd want to flip it such that you have 2 equatorial and 1 axial. Always maximize the number of groups in that equatorial position. Okay. We always have to have them. If you're asked for the most stable configuration, they should be, the biggest group should be in the equatorial position, yes. Okay, so there's a couple questions in the homework about this. By the way, the homework is due on Friday. The reason I have that is so that you have that to review all the way. You can review all the way. It'll after midnight on Friday. That's not when I would study, but you know, if you want to, you can. All 4 chapters are available for review, so you can go see what you got right, what you got wrong, and then it gives you hints on where to look in the chapter if you did get it wrong or don't understand. Okay. All right. Questions on Module 4.
Will there be situations where there are solely equatorial substituents and no axial?
Yeah, and well, you'll always have a hydrogen or two there. The hydrogens, you know, would be substituents that you would always try to have in those axial positions. Almost everything else is going to try to be equatorial. You know, but again, you have to balance the largest group. If you have two groups, the largest one is always going to be the equatorial. Okay. All right, let me go ahead and stop sharing for a second. I'm going to flip over to my review slides. All right. Hot topics. That's it. All right. Let me go ahead and share my screen again. Come on. There we go. Okay. Now, this review is based on the hot topics of each chapter, things that you must know that are fundamental to how the questions are going to be asked. Okay. Now, for style of question, look to the chapters. The book, the questions in the exam are based on those book chapter questions. So you can always look to that if, you know, so how the questions are asked, the fact that they're multiple choice, and there's no drawing, unfortunately, for this. When we get back live, maybe next year, maybe we can start doing some drawing in class on quizzes and stuff. That'll be fun. But so I'm going to hit some of the hot topics. I'm going to go through all 4 chapters in just our remaining time here, but we have plenty of time to talk about that. So the first thing that's most important is that we always fill our orbitals from the bottom to the top. That gives us our valence electrons. Our valence electrons are always the one on the outermost. If we only have our group 2's materials, we only have that second principal energy level. Once we get up into the bigger things like sulfur and phosphorus, we actually can see those third principal energy levels right here. But most of the time we're going to be dealing with those, okay? And that leads us to those different types of bonding we're going to be doing, okay? So we don't have to memorize where all these things are. Use the periodic table. There'll be 2 copies of the periodic table on the exam. One's at the beginning and one's at the end. They're the same type, they're the same periodic table, but so you don't have to go all the way up or down. You'll know by getting familiar with this table, you'll know that the 1 S's are here, the 2 S's and then 2 P's, and then we fill up from there. Now, what we can also see is that by looking down these rows, we can tell how many valence electrons we have. That's the important part about trying to build these things up. Okay, so if you are right here in your, if you're right here in, you know, your group 4A, you're going to have 4 valence electrons to deal with, okay? And you can find that with the periodic table. You don't have to memorize anything, okay? The next thing we need to remember is our trends for electronegativity, okay? This is not on the chart. You have to remember the trending of this. Obviously, fluorine is the most electronegative, and so it goes down as you come out away from fluorine. Okay. So what's electronegativity? You might want to know that. You might want to know the trend of electronegativity, and if you were given carbon and oxygen, which is more electronegative, okay? You don't need to memorize that. You look at the trend on the table of contents, periodic table, okay? Why do we need electronegativity? Electronegativity tells us about bond polarity. And when you have multiple bonds, it tells you about molecule polarity. So knowing what a nonpolar bond is, what a polar covalent bond is, and knowing what an ionic bond is going to be important to understanding the different reactions we're going to continue on with, starting with chapter 6. Because what we're going to see is the more polar the bond is, probably the more reactive it is. And so we'll probably start picking at those molecules first. Okay. So that leads us to, oops, go away. Again, Lewis dot structures, including resonance structures. Make sure you can draw a valid Lewis dot structure. Follow those rules for valid Lewis dot structures. Find all your valence electrons, put the most electronegative atom in the middle. Sprinkle everything else outside. Make sure you have all the electrons added. And sometimes, yes, you have a positive charge on it. Be able to calculate the formal charge. Sometimes you'll have radicals on them, like here, where you have an odd number of electrons. Well, that happens. A lot of times they're going to be neutral molecules. but you have to show your lone pairs. Those lone pairs take up space and control the shape of the molecule. So a valid Lewis dot structure is important. And of course, you can also have extra electrons and have negative formal charges. Okay. But notice that most of those in the negative formal charge only have that to fill out their octet. Okay. There's not more than an octet of electrons. So don't just try to make it negative by adding extra electrons. No more than 8 for most of our compounds. Okay. So hybridization controls shape. Shape tells you the hybridization. Okay. Know that sp3 always has 4 electronic zones. And if you have 4 things bonded to it, that's the difference between the electronic configuration and the molecular configuration. How many things are bonded to it? Lone pairs take up space, but don't count for molecular geometry. Now, the other thing we learned about in the acid and base chemistry is the more S-type character we have in our hybridization, the more acidic it becomes. And the key there is the S is small and spherical. The P's stick above and below it. Those S's are held more tightly. So if you have more S, those electrons are going to be held closer and closer to the middle, making it more stable to hold a negative charge. That's why hybridization also trends with acidity. Sp is more acidic than sp2, which is more acidic than sp3. Okay. So we can use our hybridization arguments for how many bonds can we form, what's the shape of the molecule, and the acidity of the molecule. All trends with that. So try to get that correlation. We're jumping from chapter 1 to chapter 3, but I want to tie those two together because that is where it comes from. All right. And of course, the molecular structure is the bonds, not the lone pairs. So don't forget, you have the molecular structure is the molecular shape is all about where the bonds are. The electron group geometry is about your hybridization. Okay. Okay, so that takes us into that. The most important part of our intermolecular forces is the fact that we are dealing with, most of the time, hydrogen bonding, dipole-dipole, and induced dipole. Okay, know that when we have these different functions, they help us with what will dissolve in what is miscible in what. And so these kind of things, if you have 2 things that have dipoles on them, they're more likely to dissolve in each other than having things with induced dipole, trying to dissolve in something that hydrogen bonds. So know the relative strength of those. Hydrogen bonding is more important, is stronger than dipole-dipole, which is much stronger than induced dipole. And again, how do you find these intermolecular forces? Hydrogen bonding, you're looking for a hydrogen bonded to an oxygen or nitrogen. Dipole-dipole, you have a valid Lewis dot structure. You're looking for lone pairs. You're looking for partially positive. Induced dipole, you only have carbon and hydrogen, non-polar bonds. So you can figure out which of these intermolecular forces by looking at the molecule, looking at a valid Lewis dot structure. Okay, and of course, within a valid Lewis dot structure, if you have more than one equivalent Lewis dot structure, then you have what we call resonance structures. Make sure that there's a couple really cool problems in the textbook about that, showing you that you can, when you calculate the formal charge of each individual resonance structure, you can end up with the average equivalent structure of this thing. Oh, well, about 1/3 of the negative charges on this oxygen, 1/3 of the negative charges on that oxygen, and 1/3 of the negative charges on that oxygen. Because when you average them out, that's what you see. That's why molecules with these equivalent resonance structures are really stable and very useful. Okay, okay, that kind of switches us into chapter 2. The functional groups that you need to know and the priority you need to know for naming things. Okay, now for this exam, yes, all of the functional groups are fair game. And the idea of which functional groups show up in which part of the IR. Okay, I don't think I included an IR slide here, but that slide where all the different types of bonds show up in your IR, that is important. Knowing that a carbon-hydrogen bond is going to show up in this zone, Knowing a carbon-carbon double bond is going to show up in this zone, and knowing that the carbon-oxygen single bond is going to show up in a different zone. That's important. You just knowing those different groups, you should be able to figure out which fragments of a functional group exist, and therefore you can help you determine which functional group exists. Okay, and we have all the different naming nomenclatures for these, and of course the priority. Again, this year we're only going to get through aldehydes, but knowing them for naming things in the future is very, and for this exam is very important. Okay, go ahead and use the nomenclature thing document on Canvas. It gives you all the rules in order. Make sure you're using the rules in the same order every single time. If you use them in the same order, you should get to the right answer 99% of the time. Okay. Okay. Know your functional groups and how to name them. We've only named the alkanes, alkenes, and alkynes right now, and that we've actually played with, but knowing how to name all the functional groups for this quiz exam is going to be a valuable tool. And of course, the basic part of every organic compound name is where that word shows up in the name. Okay, if it's a substituent, that's going to be at the beginning. The prefix tells us how many carbons are in that longest parent chain. Okay, so there you can have 50 things in front of that prefix of deca. Okay, until you get to that deca, everything else is just attached. Deca is telling you your longest chain is 10 carbons, right? The infix tells you if you have single, double, or triple bonds. Ane, ene, and ine. The suffix tells you what's the highest functional group possible. So for alkanes, it's just an E at the end. For an alcohol, it's an OL. For amine, it's amine. For an aldehyde, AL. Know these different parts of the different compounds, and you can, get your prescription out and open up that huge piece of paper, and you can start looking at the name, and you can say, oh, that's a substituent. That's a substituent. Oh, okay, here's, and then by the time you get to the 7th line of the name, that's where it actually ends up with the prefix, infix, and suffix. And so you can be able to recognize all these different things. You should be able to recognize them now, but it's actually fun. I just did that to one of my son's prescriptions recently. It was really cool. Okay. Now, the weird little group here that you need to remember a lot of is called the acetyl group, and that's the carbonyl with a methyl group on it. We base a lot of our common names on this group, like acetic acid, acetamide, acetaldehyde, acetone. They all have that acetyl functional group, and we're going to use that again and again and again. In fact, we've already used it in our resonance structures looking at that acetate ion. Okay. All right, questions on nomenclature and IR. That was chapter 2. Okay, don't forget, that if you try to memorize, well, don't memorize, but if you look at that zone chart with the CH, the OH, and the NHR, and then you see the next thing that happens is your triple bonds, and then your double bonds, and then your single bonds, know where each of those zones are. You should be able to piece all the different fragments you find together to find a functional group. And that's what the goal in IR is going to be, to answer those different zone questions as well as identify a compound based on what functional groups are there or what functional groups aren't appearing in the IR. Okay, let's see. Okay, we got a little bit of time. All right, next thing is chapter 3. Chapter 3 is acids and bases. And I told you we want to use a slightly different definition here. So the first definition we want to use is this: a Lewis acid is anything that accepts a pair of electrons to make a sigma bond, a new sigma bond. That means that a base is the opposite of that. It is donating that pair of electrons to make that new sigma bond. So this is important because even if you're not transferring a hydrogen from one place to another, like we do with the Bronsted-Lowry acids and bases, you still have this accepting of electrons or donating of electrons in the system. And the Bronsted-Lowry follows these same rules. It's just that a hydrogen is transferred in the process. Okay, and usually the part accepting the hydrogens is the hydrogen. Accepting the electrons is the hydrogen. And the base is usually the thing with the lone pair or the negative charge. So we'll see that again and again and again. All right, so how do we know which way the equilibrium is going to lie? Well, we always want to have the weakest acid, okay? Which means the strongest base always wins, okay? Because a strong base becomes a weak conjugate acid. A strong acid becomes a weak conjugate base. So the stronger base always wins, okay? So anytime you look at a reaction and you can't figure out which way the equilibrium is going to lie, find the pKa of the two different acids, the acid and the conjugate acid. Whichever one is the stronger acid, i.e. lower number, wins the equilibrium. Okay. Sometimes they're so far apart, there's almost no equilibrium, but you can almost think that every one of these reactions is in some bit of an equilibrium. Okay, so pKa's. Again, we did talk about pKb's, about that's how strong the base is, but notice the pKb and the pKa are opposite each other. Anyway, let's see. Again, the boxes here, there are several boxes on this slide. And again, this slide is on Canvas. Those are the ones I think you should know. Those are the ones that you should know, okay? I think that is the only one I might have talked about maybe knowing in class other than these would be the phenol, which is this one right here. But definitely the ones in the orange boxes. Those are the big ones. Okay. All right. So now we have four things that makes one acid more acidic than the other. We look at it in electronegativity and size. Remember, there is a trade-off there. Electronegativity, if they're all the same size, is the driving factor. The bigger the ion is, or the bigger that group is, that is the driving factor. So iodine is more acidic than fluorine, even though fluorine is more electronegative. But fluorine is more electronegative than carbon, and they're about the same size, meaning fluorine is going to be the one that's more acidic. Okay, so don't forget that we have that juxtaposition. Electronegativity first if they're the same size, and then size if they're not the same size. Resonance or delocalization of charge. That's where those valid Lewis dot structures come in. The more places you can spread that charge out, the more acidic that proton is going to be. Inductive effects. Remember, that's through bond interactions, not what the hydrogen's attached to. It's what attached a couple bonds away from that hydrogen. So that's the inductive effect. And then hybridization. Remember, I talked about that a couple slides ago. Hybridization controls the acidity, especially on carbons. The more S-like character, the fewer P's you have in your hybridization, the more acidic that carbon is going to be. Okay, and it also.
Sorry.
Go ahead.
So like electronegativity and the size of the atom, how does that how would that come into play with oxygen and sulfur, for example?
Okay, so oxygen and sulfur oxygen's right above sulfur, right? And so sulfur has that extra orbitals of the third principal energy level of electrons, meaning it's going to be bigger. That means that sulfur is going to be more acidic than the equivalent structure in an oxygen. Okay, so as we move down the periodic table in that same row, they get bigger and bigger and they become more and more acidic. Okay, does that answer your question?
Yes, thank you.
All right. Okay, so that affects the acidity. And remember that pKa, don't forget that the higher the pKa number, the weaker the acid. The more negative the number, the stronger the acid. Okay, questions about acids and bases? Okay, so I'm using, notice I'm just, these are not like practice problems or anything like that. It's concepts that you need to understand, okay? And then you can go back to the videos and look for those particular ones you don't understand. I would look at this as a template and say, okay, I don't understand these few things just based on the slides. I'm gonna go study those now. Then I'm gonna work through the homework and see if I get the answer right the first time. If I don't get the answer right the first time, maybe do a little more reading. If you get the answer right, but you got it for the wrong reason when it tells you why, say, oh, wait, hold on, I got it for the wrong reason. And so you can use that as a multiple level of studying to get you to kind of really solidify all the concepts in the correct order, okay? So that brings us to chapter 4, which is conformational analysis. We learned a new way to draw things, and that's that Newman projection. And see how drawing that Newman projection really shows you how close things are getting to each other and how far apart they can be. That's why we use it. We want to try to be in that staggered configuration or an anti-configuration if you have two other groups attached, as are more stable. And we see that there's an energy barrier of trying to rotate around. It's not too high that it can't rotate, it's just high enough that it's noticeably different. Okay. And then of course, when you have more than one group, you want to minimize the interactions if at all possible. Notice this is not just the straight up and down curve. Even in this, this position here, it has slightly higher energy than if they were anti. This anti position here is the most stable. Okay? Notice the two groups are completely opposite each other. When they're in close proximity, that's still better than eclipsed, but it's more energy than anti. And then of course, when you have two of your largest groups in that eclipsed configuration, that's going to be your highest energy conformation. And so that's your highest potential energy. And then we just finished up our different conformations of cyclohexane today. Notice that flipping from one to the other actually takes a bit of energy to do. And then it goes through all these different other configurations. But the two most important are the chair and the boat. And the other most important thing is the fact that we have chair in one position and chair in the other position. Remember, they flip back and forth with each other. But why? They flip back and forth with each other to try to have the largest group in that equatorial position or the highest number of groups in that equatorial position. Okay? And we can validate that by looking at the Newman projection of our chair configuration of cyclohexane. When we have that Newman projection right here, we only have two carbons that are in a gauche position. Everything else is in that completely staggered position. And we have little tiny hydrogens that are next to each other. And that's very little ring strain and no torsional strain. And if we did that same analysis on the cyclohexane, we see that all of our hydrogens are eclipsed and even our carbon groups are eclipsed when we go to this boat configuration, which is why it's so much higher in energy than that system. It's 30 kilocalories less stable, kilojoules less stable because of that. These staggered configurations here, here, and here. Okay. Which brings us to our last thing that we talked about is substituent size. The bigger the substituent, the more likely it's going to be in the equatorial position. And if you have to flip a ring from one configuration to the other, all the axials will become equatorial and all the equatorials will become axial in the flipped configuration. So if you drew it once where you had a big group in an axial, you'll know that you just need to flip it to the other configuration to get to the more stable configuration. Okay, those are the slides I have. Next time I do this, I'm gonna definitely put that IR slide on there. Any questions about this, cyclohexanes, the quest, I know I've learned to hate snow lately, so, but I can answer questions about that too. Okay. Exam format, good question. It is going to be on Top Hat. It is going to be multiple choice. There's approximately 30 to 35 questions. We are taking it in class time. So you, instead of coming to Zoom on Monday at 12:30, you log into Top Hat and you should be assigned one of questions. Yeah, I believe it's 30 or 35. I think it's 30. I'll have to double check, but I don't want to. So I did it while the power was going on and off. So, of the 30 questions, the total points for the entire exam will be averaged. I'm sorry, not average. The total points for the entire exam will be scaled to 130 points or 120 points as per the syllabus. So I think that makes them what, 4 points each? 30 times 4 is 120, yeah. If you want to talk to me and have me answer questions, go ahead and email me. We'll set up a time for office hours. Okay, good questions. The low pK is a strong acid. Low pK is a strong acid and will be a weak, the conjugate base will be weak, okay? So by low, we mean the closer you get to zero. Below zero is where all your really, really strong acids are. HCl, HBr are all below zero. So always think of those as our really strong acids. Everything above that is weaker and weaker. So acetic acid is our most acidic organic acid, and it's 5 points above zero. And then we get higher like alcohol and water. Those are not very acidic at all. Those are around 15. And then we go all the way up to the alkynes, which are 25, alkenes, which are 45, and alkanes, which are 50, okay? Let's see, there is a possibility to have one or two possible answers, and a partial credit will be given to that. But again, the number you'll see at the end on the exam is not your final grade, and it's out of 120 points. So don't try to scale that to see what you got on the exam. I take all the results from the exam and go ahead and analyze, throw out questions I know that you can't answer, and I'm putting in there to see that, make sure nobody's cheating. And then I'll scale it to how the class did as a whole. And I usually compare it to my past results for other classes to see if we're doing well or doing badly and we need a little more help. So don't look at that number as what you have as your grade. Will we be drawing out structures on the exam? No, it's only multiple choice. I tried to get Top Hat to let us draw structures. Their plugin for that is not very good, but it's better than sampling, but it's not very good. So unfortunately, we will not be doing that. When we get back live in class, we'll get to play with drawing a lot on quizzes. I usually have a lot of drawing on quizzes. Okay. Any other questions?
I had a question about IR. So like the specific frequencies you want us to memorize are just like the 4 zones?
The zones.
Yeah, okay.
So yeah, like 2800 to 3500, that's where all those light atoms, heavy atoms are, right? Those are all the hydrogen stuffs. And then triple bonds are next in that 2200. And then that double bonds are that, the 16 to 1800. And then below the 1500 is where all your single bonds are.
Okay, thank you.
So those just general zones, not exact numbers.
So I have a question about the one thing you said about the exam format. You said questions we can't answer. I'm kind of a little bit confused on that.
Okay, well, I'm gonna put some very hard questions on there that may have not been covered in class. Just to see if you're using some kind of cheating software. So I can read those out.
Okay. And like, what if you just
So,
accidentally guess the answer, or is it like something that you can? I'm semi-concerned about.
oh, don't be concerned. Just do your best, and
Okay.
if I get flagged by the AI and you're starting to answer questions that are plugged in there, then I'll know something's amiss.
Okay.
So don't worry, just do your best. How do you install Proctorio? I believe you go to Top Hat, it'll say install the plugin, and then it'll install, and then when you go to Top Hat again, it should allow you to immediately go to it. It's definitely a plugin, and I believe it's best on Chrome. So I would definitely try to load that up this week and get that up and running. Okay. Any other questions? We're a little over, right? We're 120. So, but if you want to hang around and don't worry if it's if you get all the hard questions right, I'll have to have a talk. But just answer the questions that look familiar to you. And we'll answer all the questions, and I'll scale the exam from there.
Just want to let you know we don't get out till 1:50.
Oh, well, okay. Well, stay behind and ask questions if you have them. That's all I had prepared for the lecture, but if you want to have questions, I'll be happy to stay behind. Why are there questions designed to get wrong? Well, according to the online teaching manual that I'm reading, it's so that you can figure out if people are just, using technology to find these. And so you put these in to gauge how people are responding. It's like when you have a survey, the best surveys are when you ask the question in a positive way and a negative way and look for the same response. So it's I don't know. I don't like it either, but it's what I'm supposed to do.
I get the point of that, but I feel like it's going to make it more likely that people would cheat if it's a question that they just can't answer. But like, at least you're giving us a heads up, which I appreciate, because then we know.
Yeah, because it's one of those things you might see it, look at it and say, I don't remember that structure at all. Okay. And if you get it right, then there's, oh, maybe you're taking it again, but that's fine. I can see that too. I can find that out. Okay, I have a question regarding group activity 2. Are we not doing that because because on Canvas it says it's due today? Well, because we were supposed to have our exam, group activity 2 is actually on chirality. So if you look at the new schedule that is posted on Canvas, the schedule, I haven't changed the assignment dates yet, but I will be changing them soon. I'll start changing those assignment dates. The new schedule that's posted there is my best guess at what we're going to do right now. Again, I say it's tentative because I have another meeting about what we can and cannot leave out of our class for this semester on Friday. So that's my tentative plan for trying to get through the semester, and we'll muddle through it the best we can. I hate keep throwing monkey wrenches in our learning, going online and going to Top Hat and being yelled at Examity and doing. I don't like changing this much, but my daughter did a project on Charles Darwin. He's like, oh no, it's not the survival of the fittest. It's the one most willing to adapt. Okay, so we are going to survive this by being willing to adapt. So bear with me and give me comments, and I'll try to adapt as we move forward.
Thank you for staying organized. It makes it a lot easier.
Oh, well, thank you. I worked very hard on Monday to get that new schedule out for my classes and try to disseminate the knowledge so that we can. I know one of my SIs was saying, I don't know what's happening in any of my classes. Nobody said anything. It's like,
yeah, that's how most of my classes were. So I much appreciate the organization on your end. It helps us out a lot.
Yeah, I was a researcher for the Navy, and I got a lot of training about communication. One of them is called risk communication, and risk communication is all about, trying to give people information without having them being scared of it. And so there's a whole bunch of ways to do that. And one is open communication, and one is, getting as much as what you know, when you know it, disseminating as soon as possible. So, and so I don't think a lot of professors here have had that Navy training. So
no, they should probably do that Navy training with everyone.
But so again, civilian employee of the Navy.
Professor Irving, there's a question in the chat asking about SI sessions, which I was also going to ask about.
Okay, the new SI sessions are times and things are posted on Canvas right now. Let me double check that. I updated the Canvas website to include, let me get to the, okay. I believe it's in announcements. In announcements, there is lecture schedule exam posted today. That's the new one right here. But then the second one there is that should be the SI sessions right here. There's a document in there. All the new SI sessions should be on there. Okay. And you should have gotten communication from, oh no, that's the old one. Okay, I will find the new one, and I will make sure it's posted on this. I know I have it somewhere.
I think I just didn't know if the SI sessions would resume today for the Wednesdays that are scheduled just because of everything that happened.
Correct, I believe that's true. I got that from Lindley as well. But I thought I uploaded this.
So the ones that are still scheduled today are still going on, correct?
Correct.
Okay.
Yeah, starting today and moving on. And don't worry about the number of sessions. We'll figure out ways we're going to extend the deadline so that everybody can get their 10 sessions in for their full credit. But just start going to your SI sessions when you would normally do them today. And then we'll definitely make sure we can do that. Oh, February 3rd.
Dr. Irvin, I had a question about miscibility and solubility. So there's a chart you showed us at like the end of the first lecture, and it kind of compares to like a solute and a solvent. So if they're like, I know they'll dissolve in each other, but there's kind of like some gray area where it's like variable solubility. So in a question, would it be like very clearly this one has hydrogen bonding and this one will only have dispersion?
For solubility and miscibility, also knowing that miscibility is two liquids and solubility is a liquid and a solid, but I hope I said that. But as far as that, it's going to be fairly obvious as to, what is the dominant interaction available to us, right? So you have something like a long alcohol. I mean, you have something like methanol and hexane.
Right.
One only has van der Waals, one has hydrogen bonding and dipole interactions. Mm-hmm. So which is methanol going to dissolve in, acetone or hexane, right? Okay, well,
acetone, yeah.
The acetone is mm-hmm. closer to it, so it's mm-hmm. going to be more likely to dissolve in that.
Okay, cool.
That's the intent.
Gotcha. All right, thank you.
Okay, and I did send something out with the new SI session times, didn't I? Because that one's wrong. I thought I sent a file out. I'll double check that. Okay. All right. Any other questions?
For the Proctorio extension through Top Hat, is that something downloading that we're going to download through Top Hat, or is that something that we go to the Chrome store, or?
It's free, and so you don't have to worry about that. I believe the easiest way to do it is actually go to Top Hat, and it'll give you a link to it, and it's just an extension that fits in Chrome.
Okay. Is it just through like the main menu on Top Hat, I guess?
I think so, yeah. Just go into Top Hat and type in Proctorio, and then it'll say, download here. It's the safest way to do it because, they're sending you to the link. So you don't have to worry about, nefarious add-ons from other people. So.
Cool, thank you.
So the way I did it was I didn't find it on Top Hat. So I just went to like Google and did Proctorio plugin, and then it sent me to Proctorio website, and then it just it gives you the link. It just says add extension here. Okay. And it quickly added it there.
Okay, that's great. Yeah, as long as it's the official Proctorio site, I think that's probably pretty safe.
Cool. Thank you.
So I had another question regarding, it's not about the test. It's on Top Hat about the questions. The first day we had class, I remember you mentioned there's attendance questions through Top Hat, but because you had difficulty issues trying to connect, but I was looking at the grades today and it shows that all of those weren't graded. And so I just wanted to make sure that I understood that correctly.
Right. And if you'll look at the syllabus, there is no attendance grade. So gotcha. It will never affect your grade. Let's put it that way first. And I was just trying it out. I was hoping to be able to do that presentation because I wanted to be a little more interactive and get feedback. And unfortunately, it was not working with my setup the way I have it. But I'm trying to figure out how to do it so when we come back live, I can actually have those embedded questions as well.
Gotcha. Okay.
But it was a grand effort on my part. It just didn't work.
Okay, thank you.
Professor Irving, I had a question for you really quickly.
Sure.
I know that you went ahead and covered the cyclohexanes and the chair and everything like that, but I just had a question over the equatorial and the anti.
Okay.
Exactly what is the anti again?
Okay. When we did just the regular straight chain alkanes with the Newman projection, okay, we had an option. We had two groups with our Newman projection on just a non-cyclic. You could have the two groups that were as far apart as possible. That was called anti. And then as the groups got switched closer to each other, they became gauche. So when they were the 60 degrees apart, that's gauche. That's the other configuration possible. And then of course we can have eclipsed. So if you look back at the diagram for butane, you'll see it go from the anti-configuration to an eclipsed, to a gauche, to two methyl groups eclipsed, to a gauche, to an eclipsed, to the anti again. And that trend right there that you're seeing is those different configurations, okay? Now, when we apply that to cyclohexanes, we just basically are drawing the same thing. We're looking for those same interactions. We're just extending it from the straight chain to the ring, okay?
Okay, I see. Thank you.
So, you know, for some people, it's like, well, how do you know which way it is? Well, you know, that's why the Newman projection is so powerful, is that you're going to say, yeah, those two groups aren't going to be next to each other. They're going to be as far apart as possible. So this has to be the answer. Okay.
Yes, sir. And then when you were talking about, I wrote down like the largest group, you meant for them to be at the edge when we do the equatorial?
Yeah, you want to be in the equatorial position if at all possible. Any large group will be at the equatorial position most of the time.
Okay, and then if they're not, then that's when we flip them?
Yes. Then
Okay.
you do the configuration and all the axials become equatorials and all the equatorials become axials.
Okay, thank you.
There, I believe there's a module on the thing that like flips them back and forth for you, and so you can see them moving back and forth. Or is that a video I saw on YouTube? There's some cool videos on YouTube, by the way. All right. Anybody else?
Yeah. I got a whole slew of questions here. I guess I can do to the end time if nobody has anything. So whenever it was in module 2.2, the IR stuff,
Right.
and then you said there's like a broad range on over like the O and U, it like went down to like 3,362. That's just because like that's just what it does.
Because of hydrogen bonding, the fact that it can hydrogen bond a bunch of different ways spreads that energy out a little bit. So let's say you're only hydrogen bonding to one oxygen and no hydrogen bonding to the two lone pairs on the oxygen. That's going to have a different frequency than if you had two hydrogens hydrogen bonding to both of the lone pairs on the oxygen and the hydrogen itself, right? So you have a whole bunch of different ways to hydrogen bond, therefore that broadens out the energies. And notice that broad peaks are only on things that hydrogen bond. The nitrogens are a little broader, the OHs are much broader, and carboxylic acids are broader and even lower in energy. So it's only hydrogen bonding things that broaden out peaks. Okay.
And then let's see. Or there's another one where it's like the characteristics, CH vibrations, and then it like increases in the
Okay. Yes. So that has to do with the hybridization. Okay. So if we don't look at the aldehyde for a second, you'll notice that all the sp3s are below 3,000. sp2s are just above 3,000, and the sps are right around 3,200. So you can actually see the hybridization change because the frequency changes. And that frequency changes because of how tightly it's bonded. Remember that sp has more s character, it's more tightly held. It's closer held to the carbon, and therefore it's a higher frequency. So your hybridization walks through that system too. The lowest energy, which is the lower frequency, is the sp3. And then as that bond gets a little bit shorter because of sp2, more s character, you go above 3,000. And then as you go to sp character, you have more s character, and it's even higher frequency, 3,200.
So, well, more S character for sp3. I thought that'd be less S character because it's like more P's, or no?
I'm sorry, did I misspeak? Because yeah, the sp3 is the longest, weakest bond because it has less S character.
Okay.
sp has the most S character and has the shortest, strongest bond, i.e. highest frequency. Okay. Remember, frequency equals energy. Or equivalent to, not equals.
Then let's see. Oh yeah, and then on these, with this little triple.
Right, that's the alkynyl hydrogen. So we're looking at that hydrogen because we're not looking at that carbon-carbon triple bond. That shows up somewhere else. We're looking at that hydrogen bonded to that sp hybridized carbon. So to have an sp hybridized carbon, it has to be an acetylene or an alkyne because you have two P's and only two of the sp orbitals available for bonding. And so that's the one that's going to be the highest frequency because it has the most S character.
Gotcha.
Now, when we look at the aldehyde, which is also on that page, you have a carbon that is sp2 hybridized, but it's bonded to an electronegative atom. So even though it's sp2 and you think, oh, it should be above 3000, that oxygen, that proximity actually brings it down in energy. And so that's why it shows it at that 27 to 2800.
Gotcha. Well, and this one is bonded to hydrogen, but if it was bonded to oxygen, that's what it would do? Is that what you're saying?
No, 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 no. On the aldehyde, which is that last functional group there, we have a hydrogen bonded to the carbon, double bonded to the oxygen.
Oh.
And yeah, that hydrogen is actually below the sp2 hybridized carbons of the alkenes because it's double bonded to an oxygen and not a carbon.
So the one that's not there, the missing is the oxygen basically from that little.
So that we're in that range. We're just looking at hydrogens, right? In that 2700 range. So those are all the hydrogens bonded to carbon we have, and they're all going to be in that 2750 to 3300 range. Does that make sense?
And yes, that makes sense. Okay. I think that was all for that. Here on the, does anybody else? Yeah, I don't know if anybody else said so. On the pKa values, like going through, well, going down, it's like alkanes and then
right,
whatever.
Right, and that goes along with hybridization as well. And those are three you definitely need to know: the alkane, the alkene, and the alkyne.
Okay.
And
so the 38 would be the alkynes.
Correct. No, 25 is alkyne.
Oh, 25 is alkyne.
Should be about 44 for alkenes, 35 to 44 for alkenes, and should be 50 and above for alkanes.
Oh, okay, that makes sense. That's right. I was missing on my last minute stuff. This is what I was going to talk to you in my office hours, but I guess why not go through it right now.
Yeah.
And then this one here, I put a question mark because something's going
down. Okay. I can't hear you. Go ahead. I see the picture.
Oh yeah.
You put it down so I can hear you ask the question. Oh. It's the paper's blocking your voice, so I can't hear you.
Can you hear me?
Yeah, I can hear you.
Sorry. Okay. Yeah, but basically.
Okay. Again, you need the paper's in front of the microphone. Just ask your question.
Which one basically? Yeah, which one? Oh, is the acid going down or something like that? And then the pKa, the value's going up. I put on here like arrows going down. Or...
All right. So your question is, how do you know which way the equilibrium lies, or what's being the acid and what's being the base?
I guess both. I guess because I'm confused now. Okay.
So when you think about, if you look at anything on your page and it has a hydrogen that can be removed to leave a negative charge, that's going to be your acid, right? And anything that was a base that now has a proton on it on the other side of the reaction is your conjugate acid. So now, which way it lies depends on which was the stronger acid, right? Because the stronger acid is the weaker base. And you want to make sure that you always end up with the weakest acid possible. It's going to shift to the weakest acid possible. So if you're comparing your pKa's, you will always be on the side of the weakest acid.
Okay.
So let's say something like water and acetic acid. Acetic acid, if you have, those are the two acids you're comparing. Like let's say you have acetic acid and hydroxide on one side of your reaction. And then on the other side of the reaction, you'll have acetate ion and water, okay? All we care about is the pK of the acetic acid on this side of the reaction and the pK of the water on this side of the reaction. pK of acetic acid is 5, about. pK of water is 15, okay? So which one's the stronger acid?
It would be the acetic acid.
Which means, which way is the equilibrium going to lie?
The equilibrium is going to go to the weak acid, so towards water.
Exactly.
Okay.
Yeah, use that argument whenever you're trying to figure it out. And if you get your pKa's right, you're going to get that answer.
Okay, actually that helps. That helped out a lot, so because I was confused. Okay, that makes sense.
Yeah, do it stepwise. You know, find the acid on one side, find the conjugate acid on the other side, find the pKa's, compare the values, and you can make a good decision at that point.
I think I just about all my other.
Sorry, grab my pin top here.
Oh yeah. So on the when I talk about base strength,
Okay, I can't hear you talking.
Acid.
Sorry.
Oh, you said it's going to the weak acid, the equilibrium, like it switches to the weak acid, right?
Correct.
Equilibrium. Okay.
And that's why on one of those slides it says the weak base, the strongest base always wins, because that will ensure that you will always have the weakest acid. So look at it one way or the other, but don't try not to mix them. Either do the conjugate acid comparison, or you look at the base strength comparison, but don't do both. You do one or the other, not both.
So it goes to the weak acid, not the conjugate weak acid, or
whichever one is the weakest acid. If it's the conjugate acid or the acid, you compare the two, the conjugate acid to the acid strength. Whichever one is the weakest, that's where the equilibrium will lie. A lot of the times when we draw this, the conjugate acid is typically the weakest, but not always. So that'll tell you the reaction might not go. If you're trying to make a very strong acid by doing the reaction, then that reaction won't go because it's going the wrong way. So we can actually see if a reaction is going to work or not by just comparing the pKa's.
Okay. Yeah, you solved all my questions right there really quickly. So perfect. Okay. All right. I appreciate you gave me up before the exam. All right. Thank you. Have a nice rest of your day.
All right. Thank you.
All right.
Anybody else have any questions? All right. I guess you're just recording, but I'm going to go ahead and end now if you don't have any questions, and I'm going to go ahead and try to post this thing today. All right. Be safe.